Hello everyone and welcome back to my channel. This video is continuation of our Qiling Framework challenges from QilingLab which we were solving, and in this video we are going to solve from challenge 6. So let's get started. Okay, so let's try to understand challenge 6 which says avoid the infinite loop. Moving to our Radare terminal using AFL command we can see the list of functions. And let's try to find challenge 6 function which is here at this offset. So by using s command, let's quickly seek to this offset. Now using pdf command, we can see the disassembly for this function. And in this disassembly, we can see that there is a for loop which is being running here. And based on this comparison instruction, it's deciding which branch to take. And in the disassembly, this is the only loop which is being shown to us. So we are sure that this is the infinite loop and we need to somehow come out of this loop to successfully solve this challenge. From this comparison instruction, we can see that it's comparing W0 with 0, and if the comparison is not equal, then it's going to this offset which is here. Let's now quickly also see the decompiled code using pdg command, and here we can see that it's just a simple do while loop with the condition always true. So by this we can say that if we somehow make the value of this W0 register to 0, then this branch not equal to condition will become false and it will come out of the loop. So one way which I can think of doing this is simply by hooking at this address and modify the W0 register the same way we did in the previous challenge, right? So if you have not yet watched the previous videos where we had solved challenges 1 to 5, then I suggest you to go and watch them first. So moving on, let's go back to our script and create a function challenge 6 and pass our killing object as argument. Then we can set our hook using ql.hook underscore address API of Qiling Framework. And if you remember, this API will take callback handler as the first argument. So let's quickly define that callback handler here. Def challenge 6 underscore callback, and let's pass this function as the first argument here, and this will be triggered whenever that particular address will be executed or emulated by the Qiling framework. Now again, just like this, we need to add the base address to this offset where we want to perform our hook in order to get the actual address at runtime. So let's create our hook underscore address variable here, and we already have our base address defined here at the top. So we have calculated it using ql.mem.get underscore lib underscore base API, and this basically returns us the base address of the binary where the Qiling framework has loaded it into the memory for emulation. So now we need to add our offset to this base address which is 0x1118, right? And then we can pass this address as second argument in hook address API, and this should trigger our challenge 6 callback. Now inside this function we need to modify our W0 register, right? So in Qiling we know in order to access a register we can do that using ql.arg.registers.register name which is x0 here, and simply assign 0 to it. Now let's call our challenge 6 function here and see what do we get in the output. And if you remember previously, the status of our challenge 5 was not solved even if we solved our challenge 5 in the previous video. But now after solving challenge 6, it's showing us the status of previous challenge as solved. So in the previous challenge, challenge 5, we made this assumption that it's not be updating its status because of this infinite loop which we have just solved now, and after solving this it's showing us the status as solved, but now still we are not able to get the output of challenge 6 in the console which might be again because we have not yet solved the challenge 7, which says don't waste time waiting for sleep. So this sleep function might be causing the issue in executing the further instructions, right? So let's try to solve this challenge now. So from the description of challenge 7, we can assume that there is a sleep function which is being called in this challenge 7, which is causing the program to wait from being executed further. So again, let's quickly go back to our Radare terminal. Let's see the list of functions. So our challenge 7 is here at this offset. So let's seek to this offset using s command and see the disassembly. Quite a small function, and indeed we can see that there is a sleep function which is being called here. Let's also try to see the decompiled version of this disassembly. So using pdg command we can see that. So here this arg1 variable, this is actually the variable or the flag which is being set when the challenge is solved. So here the challenge or the flag is already set by default, but still because of the sleep function we are not able to see the solved status. So we need to modify this sleep function in a way that this program will not get stuck because of this. So the easiest way to do this is by manipulating the argument of the sleep function. Currently -1 is being passed here, but if we pass 0, then the sleep function will have no effect and our program will be executed. So coming back to our script, let's create the function using def challenge 7 and pass our QL object. Now let's hook into this sleep function using set API method of Qiling Framework. So ql.os.set underscore API, and then as the first argument we will pass the function name which is sleep. Then the second argument would be the callback handler. So let's define it here, def challenge 7 underscore callback, and let's pass this callback function here. Now we need to somehow modify the argument to the sleep function, and obviously we need to do this at the time when the sleep function is starting, right? So in the third argument we can tell this set API to trigger this callback handler when the function is being called, right? We don't want this callback handler to be executed at the time of exit. So using ql underscore intercept dot call, we can intercept dot enter. Now in the callback handler, let's get the parameters using ql dot os dot resolve function calls params, and this takes basically a JSON object, and here we need to tell how many arguments and what are the type of the argument that this sleep function takes. So we just have one argument and let's define it as s of type integer. Now the argument to this sleep function is stored in this params object, and we can simply modify this argument using params as equals to 0. And let's print out the value of this parameter for debugging purpose, and let's call this challenge 7. Let's go back to the terminal and test the API and test the script. Alright, so now we have all the output in the console and we can see that. So in this challenge basically we are going to see how to pass the structure and how to manipulate the values of the fields inside the structure. Something similar to what we did in our second challenge. So if you have already solved challenge 2, then it would be easier for you to understand. So again, coming back to the terminal, let's list down the function using AFL command in Radare. And our challenge 8 is here at this offset, right? So let's seek using S to this offset, and using PDF, let's see the disassembly. So in this disassembly, we can see that there are some malloc functions which are allocating some memory in the stack. So we can assume that these memory allocations are being done to store the structure which we need to modify. So to get the better idea, let's try to see the decompiled code using PDG. And here we have the malloc. So memory is being allocated. 18 bytes of memory is being allocated to this PUVar1, which is of pointer type. So this PUVar1 is holding the address where the memory is being allocated. And similarly, UVar2, which is just a variable, is holding the address of the newly allocated memory of size 1E. Then this UVar2 is being assigned to pointer PUVar1. Okay, which means whatever the value pointed out by this UVar2 variable is going to be assigned to this. After that, we have PUVar1 plus 1. So most likely this PUVar1 is our structure for sure. And the first value is being set here. The second value, which is pointed out by PUVar1 plus 1, that is being set to 0x539. And then the third field of this structure is being set using PUVar1 plus 0xc, and the value and this random value is being assigned to this field, right? So from these three statements, we can assume that this structure has three fields which are being assigned here. Okay, so the interesting thing is we now know that this argv1 is the check flag, right? So this arg1 value is being stored at PUVar1 index 2. So this arg1 is part of this structure which is present at index 2. I have created a visual representation for you to better understand this. This is our memory area of 20 bytes where PUVar1 is being created, and this is our memory area of 30 bytes where UVar2 is created in memory, right? So from this statement, our UVar2 is being assigned to PUVar1 pointer. So at this place, the address of UVar2 will be stored. Then next to this variable, we have some random data which is being stored starting from the next address. So let's say if uh, the first address is 0x1000, from the next address 1001, our random data will be stored. Now we are not sure as of now what is the total length of this data in memory, so I have just assumed some random numbers, and at the next location we have our PUVar1 2 where arg1 is stored. So the memory buffer will look something like this after all the things are being initialized. So it's safe to say now that this is the structure which we are looking for, and all we need to do is to figure out in our disassembly where this PUVar1 2 is being initialized. So coming back to our disassembled code, this statement is just before the return statement. So over here is our return statement, and this is the prologue of the function, so we can ignore this instruction. And just before this we have NOP instructions, so it's safe to hook at this place to access this variable, right? And this variable is being pointed out by these instructions. So using str, the value, whatever the value is there in x1 register, that is being stored into the stack memory, right? So let's try to hook this instruction, and let's see how we can actually pass this structure. Again, as usual, let's create the function to solve challenge 8 over here. Now we need to hook at this address which is 11DC, so we need to do that by making use of our base address, then 0x11DC, right? We need to do this because this is the offset, not the actual address. So whenever the loader loads the binary, it loads it at some arbitrary address which is randomized every time. So that address we have calculated here in the form of base address, which is here at the top, and then we are just adding our offset to the base address, and this will give us the actual address. So this would be our hook address where we need to hook, and simply by using ql.hookaddress API, first we need to pass our callback handlers. So let's define challenge 8 callback. So whenever this instruction will be executed, this callback will trigger. And then in the second argument, we need to pass our address, right? Then in our callback function, we need to read the structure address which is present inside the stack. So in order to access the stack, we have the stack pointer register available in ARM64 architecture. So we will use that, and that structure is present at var28, which is stack pointer plus 0x28. So in order to read, we have ql.arc.register API and then the name of the register. So stack pointer is what we need here, and then we add the index. So starting from the stack pointer, we need to go all the way till hex 28, and this should be the place where our structure is present in memory. Now we need to read this address, right? Because in the stack, the address to the structure will be stored. So to read the address of the structure from the stack, we have ql.mem.read method, and then the first argument would be the address from where we need to read, and the second argument is number of bytes. Now we are reading the address, right? And our system is 64-bit, and 64-bit is equivalent to 8 bytes. So the address size is always 8 bytes here, so we are going to read 8 bytes. Let's typecast this output of read to something more understandable form by using ql.unpack 64. So this would be our struct address. Let's try to print this. Struct address is struct address. Let's call this challenge 8 method and see what do we get in the address field. So the struct address is this. Okay, actually this memory read API returns the output in byte form, which we don't want. That's why we have used this unpack 64 so that we will get it in the address form. Now let's read the structure from this address. So again, by using ql.mem.read, we are going to read our structure address, and we are going to read 24 bytes of this structure, and this would be our actual structure. So let's assign it to heap underscore struct variable. Now so far we know that the heap structure which we have has three fields. So let's try to unpack these three fields. So I am going to store the first field as some string, then the second field as some random data, then the third field as our check address, right? That's what we have seen in the disassembly or in the decompiled code, right? So the first is the address where these random string is stored, then some random data, and at the last, in the third field, we have our check flag. So accordingly, I have named my variables here, and now we can make use of our struct module in Python. We can import it using import struct. This module performs conversion between the Python values and the C structures represented as Python byte objects, right? So we will make use of this module to unpack the structure. And in order to do so, now we will use struct dot unpack, and then we will tell it the type. So we will use QQQ and then our heap structure. which we read just now here. So this should give us all the three fields of the structure in these variables, and let's try to print it. First one is some string. Second one is our random data, which is in random data variable. Then the third one is our check address, which is in check address. Let's run the script again and see what we get in the output. Okay, so we have all these fields here. Cool, and this is our structure address. Okay, now all we need to do is in this check address. Okay, one more thing I forgot to explain is that this is the address, not the value. And here also it gives us the hint that it's of type ulong, which mostly used for pointers. So now all we need to do is modify the value in this address, and we know that we have the right method of memory API to write something into the memory. So we are going to use ql.mem.write. We are going to write it at check address, and we need to pass it in the form of bytes. So byte 0 1, that's it. And currently our challenge 8 is not solved, but now it should be solved if everything we have done is right. Challenge 8 is solved now. Now our next challenge is challenge 9, which says fix some string operation to make the impossible come true. So this is related to some string operations. So again, coming back to our Radari terminal on the left side, we need to see where our challenge 9 function is, and it's present at this offset. So let's move to that offset and see the disassembly. Over here, we have some characters which are being passed into this src variable, I guess. Then some string copy operation is being done. After that, we have the to lower function and some loop, and again strcmp function between the destination and the source. And if w0 is equal after this string comparison, then it is doing something, otherwise it will go to either stack check field or it will just return. So to get more better understanding, let's see the decompiled version of this code, and here we get much better idea about what's going on. As we can see, first of all, we have the string copy function. This is the source and the destination. So whatever the value is in AC stack 72, that is being copied into this buffer. Then we have the for loop. So this PC stack 80 is our loop counter, and it's going to iterate over PC stack 80 till it encounters the null termination string. So what it's doing basically is just it's whatever the string is in the PC stack 80 variable, it is converting it to lowercase and then storing it into the C var variable, and that again will be assigned to PC stack 80. So in this PC stack 80, we have the lowercase version of AC stack 72, right? After that, we have string comparison where it's comparing two strings, U stack 40 and AC stack 72. So U stack 40, so in U stack 40, we have this string, right? And in AC stack 72, after executing this for loop, we have lowercase version of this string. Then if the I were to, which means if this string comparison is true, then our check variable will be set to 1, otherwise 0. So now first thing that can come into our mind is that if somehow we can make this I were value, or if somehow we return the output of this str compare value to true, then our condition will be met and our challenge will be solved, right? And that's exactly what we are going to do. So in the disassembly, let's see where our last strcmp is. It's there at 1280, and here's the comparison being made. So either we can hook into this address and make w0 to 0, or we can hook the string comparison function and modify the return value. For now, I am going to hook into this address and I will modify the w0 value to make the condition true. Okay, let's define our function to solve challenge 9. And here again we need to assign this hook address variable, and at the top we have already calculated the base address using ql.mam.getlib base API. So all we need to do now is just add our offset to this base address, and our offset is at 1284. 1284. Okay, then using ql.hook underscore address API, uh, we can hook to this address, but the first argument is our callback handler. So let's define it as challenge 9 callback, and this will be triggered as soon as the binary execute this offset. Then over here we just need to modify the register value of x0 to 0. This should solve this challenge for us. Let's see. Coming back to our terminal and execute our script, and our challenge 9 is solved. Thanks for watching this video, and if you do found this useful, then don't forget to subscribe to my channel, and I will see you in the next video.